this right here, they don't deserve to be called cos and sin.
This video has brought to you by BlenderWork, where I usually go to improve my problem solving skills and to get lesson ideas for you guys. Please visit BlenderWork/blackpenredpen.
I know you guys have been waiting for this, so today I'll show you guys why, for the hyperbolic sine cosine, they have this connections with the exponential function. And let me do a review with you guys first. For the traditional trig functions, we are on the unit circle, and once we have a point on the unit circle, we know that the x value is the cosine and then the y value is the sine. And you can do so by doing the similar triangle whatsoever, right? And let's talk about the input t. We have two ways to interpret it. The first way is the angle from the positive x-axis to the terminal side. And the second way is, this t is precisely twice as big as this area. Alright, so that's pretty cool. And now, let's move on to the hyperbolic trig functions. Instead of a unit circle, we will be using a hyperbolic for this. Therefore, hyperbolic trig functions. Starting with x squared minus y squared is equal to 1, and we just want the right-hand side. And we just want to talk about this curve. Then we pick a point, similar strategy, right? We pick a point. Then the x value is just the hyperbolic version of the cosine, and then the y value is the hyperbolic of the sine. Well, as of the input t, this time it's not the angle from here to here anymore. Although there's a hyperbolic angle, but that's a topic for another video. But anyway, the way that we can interpret t geometrically is precisely twice as big as this area. And later on, I will prove to you guys that this t is twice as big as this area. So be sure you guys subscribe and wait for that video, right? And in fact, I did show you guys why this t is twice as big as this area in the previous video. If you haven't seen that, be sure you guys go check that out. Link will be in the description. Anyway, perhaps the biggest question is that how did they come with a connection with the exponential function right here, right? For the cos and sin right here. So, it's really strange, huh? Of course, the names are similar because the work we're doing are similar. And in fact, there's also a really cool connection between the regular cosine and then the hyperbolic cosine. And also, there is a connection between the regular sine and the hyperbolic sine. Unfortunately, those connections, they are not in the real world. We actually have to go to the complex world for it. So let me do that right here. And to do so, we will actually have to utilize Euler's formula. And if you want to see a detailed explanation on this, you guys can also check out the description for the link. Anyway, I'll tell you, this right here says when we have base e, you guys can see where the e comes from, huh? And then raised to the I theta. And this right here is a complex exponent. This right here is cosine theta plus I sine theta. And now I will show you guys how we can come up with the complex definitions of sine and cosine by using this. As we can see here, the theta is our input, and the next equation I'm going to write down is that I will actually plug in negative theta to be my input. And I still have the I, and let me just put it here. So for e to the negative I theta, I just have to plug in negative I into this theta and that theta. So I get cosine of negative theta, and then we add it with I times sine of negative theta like this. Well, we see this right here, cosine is an even function, so cosine of negative theta is the same as cosine of positive theta. So let me just erase that. And because we know that sine is an odd function, so sine of negative theta is the same as saying negative sine theta, so I can just put the negative right here instead. And now you see these two equations are pretty similar, right? So we can of course solve for cosine and sine from here. Let's do cosine first. And to do so, let's just do this in our head. I'm just going to add this up so that this and that will cancel, and we will have 2 cosine theta. And it's pretty much this plus that, and let me just write that down. E to the I theta plus e to the negative I theta. And remember, we have 2 cosine theta, so we will have to divide both sides by 2. Therefore, I get cosine theta equals to this over 2. And to solve for sine from here, I will have to do the first equation minus the second equation so I can get rid of the cosine theta. Well, when I do this minus that, we will have e to the I theta minus e to the negative I theta. And be careful right here, we have positive I sine theta minus negative I sine theta. So it's like minus minus become plus. When you combine them, you get 2i sine theta. This time, I will have to divide it by 2i on both sides, so I can actually get sine theta right here. And there we have it. These are the complex definitions of sine and cosine right here. Well, that's really cool. And then I see some of you guys see where we are going. But you know what? I'm going to be mean to you guys. I'm going to erase this right here. Right? So pretend we don't know anything about that. And we're just going to work with this. So now here's the deal. On the left-hand side, both of them are real. And on the right-hand side, they are also going to be real, but they are imaginary looking because you have the eyes here, right? And I'm going to change that a little bit. I want to make the left-hand side imaginary looking, and then the right-hand side real looking. And because we know I times I is -1, that's how we can get to the real world. So this is what I'm going to do. I will just say this is equation number 1. I'm going to work with that first. I am going to let theta equal to I times some other variable, and perhaps just say t. And you can call the IT people to help you guys out right here. Anyway, the reason I want to do this is because if I plug in IT into here, yes, the left-hand side will be imaginary looking. And then when I plug in this right here on the right-hand side, you see I times this I will give me -1 and then the t. And that will make it real looking, right? Plugging IT into the theta here, so we see we will have cosine of IT. And this right here is equal to E. And this I is from the original, but the theta is now IT, and then we will add e to the negative I, and then theta is once again IT, and this is divided by 2. And now let's work this out. Here we will have e, I times I is I squared, which is -1, so I just put that as negative, and then t is t, and then we add it with, now, I times I is -1 times another negative is positive, so here we just have e to the positive t, and then this right here divided by 2. And if you would like, you can switch the term on the top. It becomes e to the t plus e to the -t all over 2, like that. And I'm going to leave this to you guys for now, and I will move to sine theta. And we'll do the same. I will plug in IT for theta. So here is that. Theta is equal to IT. Therefore, we get sine of IT. This is equal to e to the I times theta is IT, and then we minus e to the negative I times IT, and then all over 2i here. And that's clearing things up. On the left-hand side, we have sine of IT, and then this right here gives us e to the negative t, and then minus e to the positive t, all over 2i. And now, unlike earlier though, see, right here, this is imaginary looking, we have the I, and this didn't have the I. But here, the left-hand side we have the I, and the right-hand side we have the I as well. That's not cool. So what I'm going to do is, of course, we can just multiply by I on both sides, but I also want to have e to the t goes first. So let me do some factoring on the top first. Right here, let me just switch the order, so I will factor out negative, and then we get e to the t goes first, and then minus e to the negative t. And then I will say this is divided by 2. And then I will have the over I right here, so I'll just put down 1 over I like this. And this is still the same as sine of IT. And now, I'm just going to multiply by negative I throughout this equation. And we will see that on the left-hand side, we get negative I times sine of IT. This times that, I cancel, negative cancel, and we just have that, which is e to the t minus e to the negative t over 2 right here. And yes, they are really cool, isn't it? Well, I know a lot of you guys want me to put on the coach or the signature whatsoever already, but technically not yet. Because in order for us to be on the hyperbola, we must make sure we have x squared minus y squared is equal to 1. So here is the idea. I'll just make a note right here. Well, if I want to fill in the parentheses, something square minus another something square is equal to 1. In fact, you can come up with a lot of different functions to fill in these two parentheses and then make this right here true. Let me just give you guys an example. And of course, I'm not going to use constants because they would be too boring. And I will just give you guys an example. For example, right here, I can put in square root of 1 plus t. I know square and a square cancel. I just have 1 plus t. So right here, I would like to just put down square root of t. So that this is pretty much 1 plus t and then minus t, right after you cancel the squares and the square roots. This right here will give us 1. And yes, this right here will fulfill the requirement that x squared minus y squared is equal to 1. And for the people who have studied parametric equations, what we're doing is that we're just trying to write this equation in the parametric form. And the technical name for that is you find the parametrization for that. So you see, this right here is true. So you can actually call this to be x of t, and you can call this to be y of t. But in fact, this right here, they don't deserve to be called cosh and sinh. Because first, they don't have any connections with the regular sine and cosine. And second, for this t, the input t right here, they have no geometric interpretation on the curve, on the picture right here, right? So that's no cool. But don't get me wrong, if today you graph the parametric equations, letting x of t is equal to this, and y of t is equal to that, in fact, you can come up with a hyperbola. But unfortunately, this right here can only give you the top half because y is the square root of t, so that you don't get a negative portion. And maybe you can fix it a little bit, but I'll let you guys do that. That's not really the discussion here. The discussion here is the cool part. In fact, what makes this two really cool is if you put this right here, which is e to the t plus e to the negative t over 2, and then you minus this right here, e to the t minus e to the negative t over 2. This right here will give you 1 as well. And let me just do a real quick check. This right here is the difference of two squares. So what we can do is I can factor it. I can put this minus that. So as the first term, e to the t plus e to the negative t over 2. And then minus e to the t minus e to the negative t over 2. And I know I did it by a different way in the previous video, but I'm doing another way right here, so it doesn't matter. Anyway, the second part is you do this plus that, so you have e to the t plus e to the negative t over 2, and then you add it with e to the t minus e to the negative t over 2 right here. Well, let's see. You're subtracting this, right? And because they have the same denominator already, so let's focus. Here we have 2 on the bottom, and e to the t and e to the t, of course, this and that will cancel. But this minus that becomes negative become positive. So you have 2, and then you have e to the negative t, yeah? Times, same thing here, we're adding. So you see this and that will cancel, and they have the same denominator 2 already. And we have this plus that, which is 2, and then e to the positive t. And you see, of course, all the 2's cancel. In the end, you see e to the negative t times e to the positive t. Of course, this is equal to 1. Whew. So the beauty is that this right here has that requirement to be the x. And this right here has the requirement to be the y. Because when you square them and then subtract each other like this, you do end up with 1. Therefore, you can call this the x, and you can call this the y on the hyperbola. Therefore, I'm going to call this cosh t, and then we can legitimately call this sinh t, right? So hopefully you guys see the connection now. First thing is, cosh t is defined to be this exponentially using exponential function. Likewise, this is defined with the exponential function to be like that. And these two, technically, they are just a parameterization of the hyperbola. And that's so wonderful. And the connection is, cosine of it is equal to cosine of t. And then negative I times sine of it is the sinh of t. That's so cool, isn't it? Anyway, hopefully you guys all enjoyed this video, and there will be a few things I will do. In fact, I will tell you guys a few more really cool things about the sinh and cos later on in my video, because this right here is technically the even part of e to the t, and this right here is the odd part of e to the t. But as I said, that will be for another video, and I will tell you guys where this function is actually useful. And I also thank Boolean.work for sponsoring this video. And if you guys are looking for a place to have like more interesting and challenging math questions to do or to learn, be sure you guys go check out Boolean.work. They have a lot of interesting problem-solved week questions, ranging from basic to advanced topics. Some of the questions are really hard, but that's where the fun starts. And they also have a lot of interesting courses. They are designed in a really fun way. You get to learn and also have fun at the same time. If you're interested to sign up for the annual premium subscription, be sure you guys use the link brilliant.work/blackpenredpen, because that way you can get a 20% off discount with that link. And I want to thank you guys so much for watching my videos and supporting my channel. And as always, this is it.